We're going to try this again. Thankfully I didn't get very far. We're going to try this again. I don't know why I keep saying I have dropped frames. I don't know what the heck is going on, guys. I'm just going to have to do it anyway, and then just you'll have to catch it later on if it's not going to work. If you guys are seeing me okay. All right, I'm gonna, even if I drop again, I'm going to have to keep going, guys. I can't keep starting over. Okay. All right, so we were talking about nomenclature on amines. I barely got started. So for naming them as the parent, you want to drop the E and you add the amine ending if you're naming it as the parent. For simple amines, common names can be used. The general form is alkylamine. So you say whatever alkyl group you have and then the word amine. So for an example, the simplest amine is methylamine. Methylamine is a common name. So this is your common name. And then to name this IUPAC way, it's methane. We drop the E, so it's methanamine. And this is the IUPAC way. Excuse me. All right. For if you're numbering, you want to also use the N numbering like amides. We saw this back in the amides chapter. So 1, 2, 3, 4. Okay, so for this particular amine, the main thing you need to do is to start by recognizing what the parent is. Just like before, the longest continuous chain is the parent. So this is a butanamine. So putting everything together here, we have a propyl group at the N position. N-propyl, and then 1 butanamine. For that one. Another rule I want to add here is if you're naming this as a substituent, you want to use amino. So as a substituent, use amino. Like that. So oftentimes if you have these oxygen-containing groups here, these are typically priority. Higher priority than nitrogen is. So I have this particular compound that I want to name. Looking at the parent here, this is the propanoic acid. And then we have at carbon 2 an amino group. So this is 2 amino propanoic acid. Another way we can name this, remember this is, we could also name propanoic as propionic. That also works here too. So propionic acid. And then the easier way to name this one, I think, is to name it as an amino acid. This is alanine. Like that. But following IUPAC, we're going to use this naming, right? So, all right, that's pretty much it. All they want to do with the naming here. I did want to go over get into the chemistry of these guys here first. Some of the stuff is going to be a review. It should be a review from over the course of the year. Stuff that we're doing here. All right, so the first thing I want to go over with the chemistry here is the acid-base properties. All right. So it turns out that your main bases in organic chemistry are typically amines. A lot of them are anyway. So here we have some generic amine. Remember, the lone pair is acidic. Sorry, the lone pair is basic. So when you're drawing the acid-base chemistry of it, you want to show the arrow push coming from the lone pair, like so. They're typically weak bases, so we're going to show these in equilibrium. And we have that. Depending on what your R groups are, we have different names for these. So in general, if your R groups are H's, you would call this the ammonium ion. I've heard, I tend to do it myself too, but oftentimes people will say if they have like a protonated amine, people often refer to them as ammoniums also. But technically, if the R groups are carbon, this is aminium. And then what the word that I'm going to typically use in here is protonated amine. Like that. I'm going to go ahead and flip this equation just to make it a little bit more useful for something else. So we have that, and then all I'm going to be showing here is deprotonation. If you're showing just a deprotonation, this is by definition the Ka reaction. And if you were being asked to show the Ka expression for this, remember this is products over reactants raised to their stoichiometric coefficients. Like that, and then you should also remember that the pKa is simply negative log of the Ka. Like so. All right. Yeah, straight from Chem 122. All right, something I want to remind you guys of. So last semester, you guys learned that alkyl groups are donating groups. So alkyl groups donate electron density. And when we talked about this last semester, we also talked about it in this particular semester when going over the aromatic stuff and looking at directing effects on groups. But you guys, you should have seen last semester that alkyl groups, they stabilize carbocations by donating electron density towards that positive charge, like so. So with that in mind, what do you guys expect to be the effect of alkyl groups on the basicity of amines? So here I'm going to draw an amine now. Instead of a carbocation, I'm drawing an amine. Like that. And the other one I want to draw here is just with one methyl group on there. Based off the logic of what we saw over here, which one of these do you expect to be the more basic? The tertiary amine or the primary amine? Anybody want to answer that question? Which one do you expect to be the stronger base? Yes. So you guys are answering correctly. The tertiary amine is a stronger base. Like that. And it has to do with the donating properties of alkyl groups. So remember, the more alkyl groups you have on here, the stronger of a base it is. So with that in mind, let's take a look at a different type of problem that I could generate from this. So what if we have that one, so we're looking at acidity now. we're looking at this one versus this one. Which one do you think is a stronger acid? So once again, the question was, which one of these protonated amines is a stronger acid? Stronger base, weaker acid. So this is your weaker acid. This is going to be the stronger acid. Yep. So looking at greater than less than would be that. So now we can have a general trend. So we have relative basicity. You guys weren't expecting that 241 review, were you? This is all 241 review, guys. It should be, anyway. So here we're going to go ahead and compare ammonia with methylamine, with ethylamine, and then we're going to go ahead and say this one, and then the last one I'm going to put here is this one, like that. So we're looking at relative basicity. I do want to mention before we continue with this, when we look at primary, secondary, and tertiary for amines, it's a little bit different than what we saw with alcohols. For this one here, you want to basically look at the number of carbons coming off of nitrogen. So this is primary, this one's also primary, this one's secondary, this one's tertiary. And then as we saw just a moment ago, I just wrote them in increasing order. So as we add alkyl groups on there, as the alkyl groups get bigger, they become stronger bases, like that. All right. And then what do you guys think about this one here? What about this one? This is a quaternary amine. Would you expect a quaternary amine to be basic? Right here. So are quaternary amines basic? No, that is correct. Quaternary amines are not basic because that lone pair is not available. So these are not basic. And the reason why is because no lone pair electrons. You need those lone pair electrons for it to work. All right. So another thing I want to talk about here is that the resonance, if the lone pair is in resonance, this can have a huge impact. So resonance of the lone pair impacts basicity. Like so. So here I'm going to have a primary amine with just a regular ring on it, like that. Versus that one, like so. So for this one here, the lone pair is in resonance with the ring. So this is a weaker base than this one. This is a much stronger base. And once again, the reason why is because the lone pair is in resonance. All right. If you were comparing this one, like that, it turns out that you have a donating group in there. Donating groups will increase electron density So EDGs on anilines will increase basicity. So I'm going to add that comment here. EDGs on anilines increase basicity. So if you were comparing these two, it would be like that. So I have a question I'm going to leave you guys with that I want you guys to answer on your own as homework. You guys love doing homework, right? So the question here is, which is a stronger base? And to answer this question, you're going to have to draw resonance. So you can have some good resonance practice. So we can have this compound versus this one. So all I'm doing here is they're the same compound. All I'm doing is I'm moving the nitro group. So what I would do if I were you is draw resonance structures of this and look at the availability of the lone pair. Is it more available in one or the other? If the lone pair, if it's going to work out, the one that has more resonance structures is the weaker base out of the two here. But I want you guys to figure that out for practice. All right, the last thing I want to talk about with amines is more of like a real world use of this acid-base chemistry that people see in their daily lives. So here we have an amine. And then you guys might remember last semester when we were doing the acid-base extraction lab. We had a lab where we basically would protonate this to make it water soluble, and then you would deprotonate to make it go back to being insoluble. So what I'm going to go ahead and do here is just write HCl plus HCl, and then we're going to get our aminium like that. All right, so it works out where if you have your free amine, that's what these are typically referred to as, a free amine. These typically end up being volatile, meaning they give off they have a high vapor pressure, they give off a lot of odor typically. And these also typically end up being insoluble in H2O. All right, here we have the aminium HCl salt. Typically, ionic compounds are oftentimes non-volatile. So this is non-volatile. Additionally, this is soluble in H2O. So once again, to summarize, we did this chemistry in lab during 241 last semester, where we had an amine compound dissolved in ether. We treated it with HCl to put it into the aqueous phase. You then treated the aqueous phase with base to bring it back to this form, and then you filtered it out. If you have really good memories, that was the yellow compound in the extraction lab during the acid-base extraction lab. Another way this is commonly used is it turns out that a lot of fish odors out there, like fishy smells in the fish case at the grocery store, a lot of them are amine compounds, and treating them with lemon juice, which is citric acid instead, achieves the same result. So if you go to the Albertsons and they have like lemons in the fish case, oftentimes they're doing that to keep the odor down, and that helps by making this not as freely available. All right, so because I like talking about drugs, I have a drug compound to put up here for you. You guys always like this part of the discussions. So here I'm drawing this kind of weird looking, but I wanted to put emphasis on the amine. Wow, someone just posted a picture from that lab from their phone in the Discord. That's awesome. But yeah, that was the amine compound in that particular experiment. All right. We got this compound. I'm drawing it kind of funny looking, but it'll be fine. All right, give me 1 second, guys. 1 second. Just making sure I got my structure right. Yep, that's right. Okay. All right, so here we have an amine compound. If this compound was treated with HCl, do you think it would be soluble or insoluble in water after it was treated with HCl? So if we protonate this, is it going to be soluble in water, insoluble in water, or you can also ask, is it going to be volatile or not? Yeah, so if you treat this compound with HCl, it becomes water soluble. It basically becomes that form. So this particular compound has the common name of cocaine. If you're taking the organic lab for majors, they back in the day during the organic lab for majors, they used to make cocaine in the lab. That lab has been replaced with lidocaine instead, but the chemistry is similar. It turns out that when cocaine occurs naturally, hey, Breaking Bad with methamphetamine, not cocaine. But it turns out that the naturally occurring form of cocaine is the aminium form. This is the naturally occurring form. And what people will do is they'll take this and treat it with baking soda. And so if you have the protonated version, treating with baking soda makes it the free amine. And what that does to it, it makes it non-volatile. It makes it easier to smoke. So that's actually some of the chemistry is done with methamphetamines also, but this is very, very commonly done with cocaine. And it turns out that if you have the free amine form, there are two names people use for that. If you're talking about cocaine, people often refer to that as free basing is one term people have used before that. They're referring to the free base here. Another term people use for this form of it is crack. So if you ever heard of crack cocaine is the deprotonated form of regular cocaine. And because of the fact it's more volatile now, when you smoke it, you get a much more potent high off of it because you're getting a lot of it, more of it's going into your brain than this form would if you were to smoke it. So there's your drug chemistry for the day. Your obligatory drug talk for the day. All right. So the next part here, we are going to be Breaking Bad. We're going to be preparation of amines. So preparation of amines. Yes, the baking soda is what's used. All right. So asking for a friend, huh? All right. We actually have done a lot of this stuff already. I think there's only one actually new reaction here. Well, we have done this before in the past. So I want to go ahead and show this first one here. So this is alkylation. Of ammonia. So here, what I have here is I have ammonia, and I have a primary alkyl halide. So ammonia, And then here we have a primary alkyl halide. And then, as you guys probably saw last semester, at least you should have, is this is going to undergo an SN2. So backside attack, like that. You kick out the leaving group. You have that. And then what you can show here is another mole equivalent of ammonia deprotonating. All right. So the question I have for you guys now, look at the comments here real quick. Oop, did not want to open Steam. Hang on, I opened Steam on accident. All right. So based off the two compounds that I have here, so I started with ammonia. I then made a primary amine. Which of them is a stronger nucleophile? Ammonia versus this primary amine. So once again, the question was, which one is the stronger nucleophile? Yes. So this one is a stronger nucleophile. So what ends up usually happening here is multiple alkylations often occur because we made a stronger nucleophile. So multiple alkylations are likely unless excess ammonia is used. So once again, what happens here is we have that and ammonia makes that. This could then react with another equivalent of this one, giving us that. This could react with another equivalent of this one, giving us that. And then it could react with another equivalent of this one, giving us the quaternary amine. Like that. So it goes from being primary, secondary, tertiary, quaternary. All right. To avoid this, we use the Gabriel synthesis. So use Gabriel synthesis looks like a stick figure. It does. All right, so if you guys want to specifically make a primary amine, you're going to have to use what we call the Gabriel synthesis. So yet another named reaction. We have a couple named reactions actually in this chapter. All right, so one sec. Scroll. All right, so let's go ahead and take a look at the Gabriel synthesis. I think we're actually going to get to where I wanted to today. All right. So this has a really specific starting point. You guys might remember that we worked with this compound a little bit during the last set of material. We have this compound. This is called a phthalimide. So we have a phthalimide. The way you want to pronounce this word is don't say think the pH is silent. So it's this phthalimide. Don't say the F sound. What we do here is this is treated with KOH. And I do want to mention here that the pKa of this particular H is about 4. So this will deprotonate. So I'm going to use green for this. So deprotonation. Like this. And then now what we do here is now you do your SN2. This compound is gonna make a version that will not keep reacting. So this will do your backside attack like that to your primary halide. We now have that. I think I'm off screen. Let me double check. I think I'm off screen. There we go. Like so. All right. So now what we need to do is we need to kind of just release this part. So your primary amine's kind of embedded in there. Do you guys have any idea of what I can do now to basically release this part? I want to get this part out of here. What reagent can I do? I have 2 things in my notes here for it. One of them you guys should know. Resonance stability of this anion. So the question was about the acidity of this. This is resonance stabilized. Typically amides are not very strong acids, but this one happens to be acidic. Yep, so what I have here in my notes is water, H3O plus and heat to basically get rid of this thing. So let me draw the products here. So that ring is going to pop open and we're going to have these 2 groups are going to be carboxylic acids. Like that, and then we have our primary amine released. Like so. Double check. All right. So let me, starting like that. And then this particular reagent here is that particular compound. You may see it written as N2H4. I've seen it written that way. This is hydrazine. All right, so what this is going to do, it's going to do an acyl substitution. And these 2 N groups are going to be plugged into this compound. Like that. And we have H and H. And then our side product is the one of interest, is our primary amine. So either one of these work after you. So once again here, you're going to deprotonate to make a nucleophile, SN2, and then either one of these reactions releases the primary amine. All right. Any questions about the Gabriel synthesis? All right, I got a few more reactions I wanted to go through here, guys. Where did the 3rd carbonyl? Oh, I don't know where it came from. I just randomly added it. Yeah, good catch. Yeah, that carbonyl was not supposed to be there. All right. That was an oopsie. All right, so Poof chemistry. All right, so next particular, yeah, that's the impossible chemistry there. So the next one I have here for you guys is synthesis with sodium azide. So we have a new reagent here to work with, and this is NaN3. All right. So what I'm doing here now is I'm just drawing your azide ion out. Based off the formula here, overall it should be a -1. And we're going to see that here. Looking at the formal charges on each of the nitrogens here, the formal charges on this nitrogen is -1, this one is +1, and this is -1. So there is your overall -1 charge. And it turns out that these particular ions are good nucleophiles for SN2. So I think I show this to my class when we do the SN2 stuff. But here I'm going to go ahead and draw an SN2 with the methyl iodide. So this is going to do your backside attack. Kick out the leaving group. And then what do we have? We have N double bond N double bond N methyl. Overall it's neutral now. Like that. And then what we do here is do a reduction with LAH, and we now have methylamine. Are we Breaking Bad? We just made methylamine. Oh my goodness. It's one of the ingredients. Methylamine. All right. So other ways to make amines. So that's one way. So we have the using sodium azide works. SN2 followed by reduction. We have seen reduction of nitro compounds before. Reduction of nitro compounds. So you guys should know this one. All right, so tin or zinc and HCl was one way. I think another way we showed this was LAH does this also. Like so. All right. I think I have one more way. Let me just double check it. One or two more ways. We got a couple more ways. We're not quite done yet. I was thinking we were done almost. All right, so another one we talked about earlier this semester, at least I know I did in my class, was reductive amination. Now, you guys were mentioning Breaking Bad earlier. If you actually go back and watch the show Breaking Bad, they specifically mentioned this reaction is what they're using to make methamphetamine. And for those of you guys that were in my class, we went over this. I think we went over the how to make methamphetamine from benzene. That was a fun one. That should be in your notes. I like to do a little bit of review here because we did do some nitrogen chemistry earlier this semester. This was during the aldehyde and ketone chapter. So aldehyde or ketone. All right, so here I'm going to go ahead and show what do we get if we get ammonia or react ammonia. Oops. We get that. And then here I'm going to go ahead and use methylamine. You guys remember this chemistry at all? We did this chemistry a little bit last semester, or earlier this semester. These particular compounds are called amines. So IMINE. The first one we're using ammonia. The second one we're using a primary amine. Like that. The second one here, I'm going to use a secondary amine. And then the last one I'm going to do is a tertiary amine. Like that. So if you're using a secondary amine, we get the ene amine. That. And then do you guys remember what happens with the tertiary amine? Does this reaction work? Does that reaction work here? So we have a tertiary amine plus an aldehyde or ketone. Does anybody remember if that works or not? Yep, we get no reaction. I didn't go over it in a lot of detail in lecture, but I do want to mention here that enamines have similar chemistry as enolates. They look kind of like an enolate here. But anyway, so after you have your amine or enamine, if you do a reduction here, these will become amines. So here I'm just going to put generic H, and then I'll show you what these are below. So this one here is going to give us this amine. This one's going to give us this one. And then this one, reduction again. Like that. So let me move my face over. Oop. Wrong one. There we go. All right. So do you guys have any questions about this so far? So a little side note here. Reduction can be a couple different things. We have a couple different ways we can do this. This can be LaH, NaBH4, H2 palladium, and then we have a new one here that I want to mention here is this one I have in my notes, is also a reducing agent, plus others. All right, so more drug talk today. So you guys like hearing the drug conversation here. So one of the bad parts about making methamphetamine is the reducing agent is hard to find. So it turns out that if you go out there and look at all the different chemicals that you can get, like at Home Depot and like at all the different stores out there, oxidizers are very easy to find. Oxidizers can be found at Albertsons, like OxyClean, hydrogen peroxide, hydroxide, all that stuff is available at Albertsons and any other grocery store. Reducing agents are the challenging part. So one thing people have done to get a reducing agent for making illegal methamphetamine is they'll take the lithium out of batteries and strip the lithium out, and that lithium metal can be a reducing agent. And that's pretty nasty chemistry. I wouldn't want to be ingesting any of that stuff. But oftentimes when people make that dirty meth, all these other chemicals that are in there is what makes it even worse than the regular stuff. If you guys want to try the Breaking Bad question, I'll go ahead and give you the structure. So the question I gave, those in my lecture have this in your notes already, but it was starting from benzene, make methamphetamine, which is that. That's your methamphetamine. Going backwards a step, the way we did it in our notes, we made that first. I think we used an epoxide. We did an epoxide, then an oxidation to do that. And then we did reductive amination to end it. Another thing about the Breaking Bad show, they also specifically mentioned phenylacetone at 2 points during that show, which is this compound. This is phenylacetone. So first we did crack and cocaine. Now we're doing methamphetamines. Amines are cool. Do you guys have any questions about the reductive amination method? Any questions? All right, I think I have one more reaction for you guys, and I'm out of time. I wanted to wrap up at 1 o'clock today. We are not done with the chapter, though, by far. I do have more stuff to go over. But let's just go ahead and do one more way to make amines, and then we'll end class here. So it turns out that we can also do a reduction of nitriles, oximes, and amides. We've seen these two before, the nitriles and amides reduction. We have not seen what an oxime is yet. All right. This particular compound is Phaedo Nitrile. This is a common solvent that's typically used. We don't use it a lot in this class, but I do want to mention that out in the greater world out there, this is a common solvent that's used out there. And it turns out that if you could do a reducing process on this one, and it's done with sodium metal and ethanol. This is a reduction, and you're going to get ethylamine from this. Like that. The next reaction I have to show you guys is the oxime. So this is your oxime. Like that. The reducing agent for this one here is rainy nickel. I believe you saw rainy nickel before. Rainy, basically, it kind of means it's granular. So this is the type of nickel it is. The grade of it, essentially. All right. And we saw this one earlier today, LAH. And these are all making ethylamine for all of these. All right. Yeah, the next reaction I wanted to go over, we still have to go over the Hoffman rearrangement and the Curtius rearrangement. And we did the Hono reactions already. And then I also wanted to go over Hoffman elimination, which is more review from last semester. But we are actually at a good stopping point, guys. We've been going for about an hour now. Does anybody have any questions about anything? Any questions? All right, I do want to mention that I don't take any responsibility for anything that you do from this content. That's at your own risk. I don't recommend making your own crack or methamphetamine in your garage. Yes, there is going to be a quiz on amines this week. So the question was, is there going to be a quiz on amines? Yeah, the next quiz is going to be phenols and amines. Phenols and amines will be the next quiz. All right, guys, I'm going to cut the stream here. Are you guys interested in doing a Zoom? We'll see. We'll talk about that in Discord. But I'm going to go ahead and cut the stream here. This week it'll be up. All right, guys. Talk in Discord.